And we're now back to another category or type of noise. So this type of noise has a power spectrum that resembles the thermal noise, having an equal energy in every hertz of bandwidth at frequencies from DC into gigahertz. So, however, the mechanism that creates shot noise is different. Shot noise is due to random variation in current flow in active devices, such as tubes, transistors, and semiconductor. So that is some example of the active devices. So these variations are caused by the fact that current is a flow of carriers, each of which carries a finite amount of charge. So current can thus be considered as a series of pulses, each of consisting charged current by one electron. So shot noise is usually represented by current source, this equation here. So the noise current for either vacuum or junction diode is given by this equation. So IN equal to square root of 2QIO times B, where IN equal to RMS noise current in amperes, U equal to magnitude of charge on an electron, which is equal to 1.6 times 10 to the power of negative 19 coulomb. Then IO, the DC bias current in the device in amperes, and B, the bandwidth over which the noise is observed in hertz. So here is an example of problem involving shot noise. So let's read. A diode noise generator is required to produce 10 volts in a receiver with an input impedance of 75 ohm resistive and a noise power bandwidth of 200 kilohertz. What must the current through the diode be? So what is the value of IO? The solution is first convert the noise voltage to current noise. Convert the noise voltage to current. So using Ohm's law, we have IN is equal to Vn over Rn. So given Vn equal to 10 volts and Rn equal to 75 ohms, therefore IN or the noise current is equal to 0.133 microampere. How about the current through the diode? So using the equation given earlier, so we have IN equal to square root of 2Q IO times B. So multiplied it to the power of 2. So we have IN squared 2Q IO B. So solving for IO, we have IN squared over 2QB. So IN is 0.133 microampere squared. 2 times Q is equal to 1.6 times 10 to the power of negative 19 coulomb times the bandwidth, which is 200 kilohertz. So solving for IO, we have 276 milliampere. So that is our value. So another type of noise is partition noise. Partition noise is similar to shot noise in its spectrum and mechanism of generation, but it occurs only in devices where a single current separates into or more paths. An example of such device is bipolar junction transistor, where the emitter current is the sum of the collector and base current. Another type of noise is excess noise. It is also called flicker noise or 1 over F noise. Sometimes it is called pink noise because there is proportionality of more energy at the low frequency end of the spectrum than with the white noise, just as pink light has a higher proportion of red than does white light. Another type of noise is the transient time noise. Too many junction devices produce more noise at frequency approaching their cutoff frequencies. This high-frequency noise occurs when the time taken by the charge carriers to cross a junction is comparable to the period of the signal. Some of the carriers may diffuse back across the junction, causing a fluctuating current that constitutes noise. Since most devices are used well below the frequency, these transient time effects are significant. This type of noise is not usually important except in microwave devices. Okay, all of the noise sources we have looked at have random waveforms. The amplitude at a particular time cannot be predicted. Although average voltage is zero and the RMS voltage or current and the average power are predictable and not zero. Signals like this are said to be uncorrelated. That is, they have no definable phase relationship. In such case, voltage and currents do not add directly. But the total voltage of series circuits or current parallel circuit can be found by taking the square root, this one, of the sum of squares of individual voltage or currents. Another problem here, the circuit below shows two resistors in series at two different temperatures. Find the total noise voltage and noise power produced at the load over a bandwidth of 100 kHz. Actually, the voltage across this load is just 1/2 of this noise voltage generated by this two resistor series combination. So first, we have V in over 2. So let us first solve this noise voltage generated by these two resistor. So we have Vn is equal to the root mean squared of the 2. So we have Vr1 squared plus Vr2 squared. So solving it, so first determine the equation. So substitute the formula of Vr1 for the noise voltage. So we have square root of 4 kT Vr1 squared plus 4 kT Vr2 squared. Then let us cancel out the squared here, square root. Cancel out the square root. So what we have left is 4 kT Vr1 plus 4 kT Vr2. So extract or separate the common terms here. What is the common among the two? So we have 4k and b. So 4k b times t1 R1 plus T2 R2. So substituting the values, so we have 4 times 1.38 times 10 to the power of negative 23 joules per Kelvin, and the bandwidth is 100 kilohertz times temperature of 300 times 100 ohms plus 400 Kelvin times 200 ohms. So what is the value? So using our calculator, calculate these values. So what we have here is 779 voltage. Then 1/2 of that is approximately the voltage at the load, which is 779 divided 2 or 780 approximately. It is equal to 390. Okay, this is 779 nanovolts. So divided by 2, so we have 390 nanovolts. So that is the voltage across the load. Another problem is compute the noise power produced at the load. So we have already solved the voltage, and the resistance is given also. We have 300. So just use the one of the equation for Ohm's law. So we have power is equal to V squared over R. So what is the voltage at the load? So we have 390 nano volts squared over the resistance, which is 300 ohms. So computing it, so we have the power equal to 500.506 femtowatts. So that is the power at the load. Actually, the main reason for studying and calculating noise power or voltage is the effect that noise has on the desired signal. In analog system, noise makes the signal unpleasant to watch or listen to, and in extreme cases, difficult to understand. In digital system, noise increases the error rate. So in either case, it is not really the amount of noise that concerns us, but rather the amount of noise compared to the level of the desired signal. That is, it is the ratio of the signal to the noise power alone. This signal to noise ratio is abbreviated as S over N and usually expressed in decibels. So it is one of the most important specifications of any communication system. Typical values of signal as S over N range from 10 decibels to, that is for barely intelligible speech, and range up to 90 decibels. Okay, 90 decibels for more compact disc audio system. Another sample problem here is a receiver produces a noise power of 200 milliwatts with no signal. Okay, the output level increases to 5 watts when a signal is applied. Calculate the S plus N over N as a power ratio and in decibels. So given that the signal plus noise, so the output is composed with the signal plus the noise is equal to 5 watts, and the noise itself is 200 milliwatts, so 5 over 0.2, so we have 25. Then in decibel, this is just the 10 log of that ratio. So calculating in dB, so review your logarithmic properties. So calculating in dB, so we have 10 log of the ratio, so we have 14 dB. Since a thermal noise is produced by all conductors, and since active devices add their own noise as described previously, it follows that any stage in communication system will add some noise. An amplifier, for instance, will amplify equally both the signal and the noise at its input, but it will also add some noise. The signal-to-noise ratio at the output will be lower at the input. Noise figure is occasionally called noise factor. Noise factor. Sometimes the term noise ratio is used for the simple ratio. Noise figure, noise factor, noise ratio. So we have the following formula here for noise figure. So we have the signal to noise at the input side, not in dB, just a ratio. Then over signal to noise at the output, also in ratio, not in dB. So for calculating in dB for noise figure, just when given in dB, so just subtract the output signal to noise from the signal to noise in dB. If given in ratio, just 10 log of noise figure. Now, let us solve some example. So the signal power at the input to an amplifier is 100 watts and the noise power is 1 watt. At the output, the signal power is 1 watt and the noise power is 30 milliwatts. What is the amplifier noise figure as a ratio? As a ratio, not in dB. So first determine the signal to noise at the input, which is equal to signal is 100 watts over the noise is 1 watt. So we have signal to noise at the input equal to 100. How about the signal to noise ratio at the output? So we have the signal of 1 watt over 30 milliwatt. So we have 33.3. So solving for the noise figure, so we have signal to noise at the input over signal to noise at the output. Solving for the ratio, so we have 100 over 33.3, so we have 3, a noise figure of 3. Okay, another way of specifying of the noise performance of a device is using equivalent noise temperature. The noise temperature has nothing to do with the actual temperature of the circuit. Rather, as shown in figure 3 here, it is the absolute temperature that is connected to the noiseless amplifier of the same gain would produce the same noise at the output of this ideal real noisy amplifier. So we have the noise figure as a recap. So noise figure is equal to signal to noise at the input over the signal to noise output. So rearranging them, so we have SI over SO times NO over NI, where SI is the signal power at the input and Ni is the noise power at the input, then So is the signal power at the output, and No is the noise power at the output. If we're going to refer all amplifier noise to the input, then this noise as well as the noise from the signal source will be amplified by the gain of the amplifier. So let the amplifier power be A, capital A. So let this be our gain, the gain of the amplifier. So the noise from the input and the noise from the signal noise will be amplified by this gain of the amplifier. So A is equal to signal out over signal in. That is the gain. Substituting this to the previous equation with NF is equal to SI over SO times NO over I. So we have noise figure is equal to 1 over A NO over Ni. Therefore, the noise at the output will be NF, the noise figure, times the noise at the input times the gain. So that is our noise at the output. Thus, the total noise at the input will be NF times Ni. So this one this one will be our noise at the input, NF times Ni. Let me change the color. Okay. So the equivalent input noise generated, first let us assume that the input noise is a thermal noise. So since the input source noise is a thermal noise, therefore, let me change the color. Okay. No, not the same color. Where is the color? Red. Is the color? Yeah, that is the color. I'm finding. Okay, let me erase it first. So this one is the source at the input. Like a statement. This is the noise at the input. And then assuming the input source is a thermal noise, so we have Ni is equal to K E B. Okay? So the equivalent input noise generated by the amplifier must be, so what is the equivalent noise generated by the amplifier when our noise at the input is equivalent to NF minus Ni? So, N equivalent at the amplifier is noise at the input source, so we have NF times Ni minus the thermal noise, which is Ni. So that is the equivalent noise at the amplifier generated by the amplifier. So let us substitute the value of Ni. So Ni is equivalent to KTB. KTB minus KEB. So therefore, our equivalent noise at the amplifier will be NF minus 1 KTB. So that is our noise at the amplifier. If we suppose that this noise is generated in a resistor at temperature T equivalent, and we further suppose that the actual source is at reference at 290 Kelvin or 27 degrees Celsius. So therefore, we have K, the noise, okay, KTB equivalent is equal to NF minus 1 KTB. Therefore, what would cancel out? We have K, B, E. So what we have left here is T equivalent is equal to NF minus 1 PO. And assuming that our temperature is at room temperature value, typical value of temperature 290 Kelvin or 27 degrees Celsius. So we have T equivalent is equal to NF minus 1 290. Okay, so that is our T equivalent. So the result is actually trivial, easy to understand, and expected. Because it turns out the T equivalent can be found directly from the noise figure and thus contains new information about the amplifier. However, the T equivalent is very useful when we look at the microwave receivers connected to antennas by transmission line. The antenna has a noise temperature due to largely to space noise intercepted by the antenna. The transmission line and the receiver will also have noise temperature. It is possible to get an equivalent noise temperature of the whole system by simply adding the noise temperature of antenna, transmission line, and receiver. From this, we can calculate the system noise figure by rearranging. So rearranging this value, we will get the noise figure equal to, what is the value? T equivalent over 290 plus 1. Okay? So we can get the noise figure directly from this equation. We have an example here. Sample problem. So an amplifier has a noise figure of 2 decibels. So the question is, what is its equivalent noise temperature? So we have the solution here. So it is finding the equivalent noise temperature. So recall that noise at T equivalent or the equivalent noise temperature is equal to 290 times NF. NF here is in ratio. So we must find the noise figure in ratio. Since we are given a noise figure in decibel, let us convert it first to ratio. The noise figure in dB is equal to 10 log of noise figure in or ratio. So finding the noise figure in ratio, so we have anti-log of NF in dB over 10. So that is how we get the NF ratio. So if you're finding hard to convert this, just please review your logarithmic uh, equations. Okay. So I think I don't have to elaborate it because I know it is covered in your previous subjects in math. So the noise figure ratio is equal to anti-log of NF, which is 2 decibel over 2 divided 10. So we have anti-log of 0.5, 0.2 rather, sorry, 0.2. So anti-log of 0.2 is equal to 1.585. That is our NF in ratio. So we already find the noise figure here, 1.585. So now, let's say this is equation 1. So now let us substitute this noise figure ratio into this equation 1. So P equivalent is equal to 290 Kelvin times 1.85 minus 1. So our T equivalent, or the equivalent noise temperature, is equal to 169.6 Kelvin. So that is our equivalent noise temperature given a 2 decibel noise figure. When two or more stages are connected in cascade or in sequence, as in a receiver, the noise figure of the first stage here is the most important in determining the noise performance of the entire system, because noise generated in the first stage is amplified in all succeeding stages. So this noise will be amplified in all succeeding stages. Noise produced in later stages is amplified less, and noise generated in the last stage is amplified the least of all. While the first stage is the most important noise contributor, the other stages cannot be neglected. It is possible to derive an equation that relates the total noise figure to the gain and noise figure of each stage. So in the following discussion, the power gains and noise figures are expressed as ratios. Okay? So just take note, in our following derivation, noise figure here will be in ratios, not in decibel. So first, let us recall the noise power in the input is equal to K T B. Then accordingly, the noise at the output of the first stage will be NO times the noise figure, then the noise of the input, and the gain of the first stage. So that is the noise output power of the first stage. So this noise appears at the input of Kenisha, mo appears sa input sa second stage. It is amplified by the second stage and appears at the output multiplied by A2. So first, what is the equivalent noise in stage 2? So we have NEQ at 2 is equal to noise figure of 2 minus 1 times KTB. So just recall the previous derivation on how to compute the noise figure of the second stage. So as I've said, the noise appears, the noise output of the first stage will appear in the second stage. So it will be amplified in the second stage, then it will be multiplied by the gain of A2. So the noise output of the second stage is equal to NO2 equal to the noise output in first stage plus the noise output of the noise equivalent at the second stage, NAQ2 times the gain of A2. So let us substitute the values of NO1 and NAQ2 here. So NO1 here is equal to NF, the noise figure, then NI times A1. Then what is the equivalent of NAQ2? We have noise figure 2 minus 1 KTB times A2. And take note that NF, NI, or NI rather, is equal to KTB. So therefore, NA2 here is equal to NF times KTB. That is the equivalent of N1, NI times A1 plus NF minus 1 KTB A2. So finding the common factors here, so we have KTB and KTB. So we have NA2 is equal to KTB A2 times noise figure 1. Why am I always forgetting 1 here? NF1 plus NF2. NF2 minus 1. So we have the output noise KTB-A2 times NF1 A1. I forgot A1. A1 plus NF2 minus 1. So to clarify the writings here, let me write it here again. The output noise of the second stage is equal to KTB A2 times noise figure of 1 A1 plus noise figure of 2 minus 1. So that is the output noise of the second stage. So now we are going to find the noise figure for the entire system or for the whole system. So we have NFT equal to noise at the output of second stage over the noise at the input stage and the total gain. Note that the total gain is the product of the gains of the system. So we have the gain of the first stage times the gain of the second stage. So to derive for the total noise figure, substitute the values of NO2 output noise of the second stage and substitute the value of Ni1. So we have K, T, B, A2 times NF 1A1 plus NF2 minus 1 over noise figure of the first stage K, T, B times the total gain. So we have A1 and A2. So we are going to cancel the common terms. Do we have common terms here? KTB A2, KTB and A2. So what we have left is NF noise figure total is equal to NF 1 A1 plus NF 2 minus 1 A1, right? Then we can simplify it. So we have equal to, this will cancel out for this first term. So we have NF1 plus NF2 minus 1 over A1. This is N. So this will continue here. So for this equation known as Freese formula can be generalized to any number of stages. So if we have numerous stages, we can have this general equation of Freese law. So we have NFT equal to NF1 plus, let me erase some to emphasize. Okay, NF1 plus NF2 minus 1 over A1, then NF3 minus 1 over A1 times A2, and then so on and so forth. Okay, so this is the Freese formula. So we have an example problem here. A three-stage amplifier has stages with the following specifications. So with this following specification, calculate the power gain, noise figure, and noise temperature for the entire amplifier, assuming match condition. So first, let us compute the power gain. So power gain is just the product of all gains of the corresponding stages. So total gain is A1 times A2 times A3. So therefore we have 10 times 25 times 30 equal to, calculating it, we have 7,500. When in dB, so the gain in dB is, in dB, 80. So 10 log of 7,500 is equal to, what is the value? It is equal to 38.8. So 38.8 dB. So that is the total gain. Next is, what is the noise figure of this amplifier? Okay, let us take note first. Okay, let us take note our answer here. So total gain is 7,500. For in dB, we have 38.8 dB. So for okay. So now let us compute for the noise figure. Okay, now let us compute for the noise figure using the freeze formula. So we have NF is equal to NF1 plus NF2 minus 1 over A1 plus NF3 minus 1 over A1 times A2. So we have noise figure of stage 1 is 2 plus noise figure of 2 is 4 minus 1, and the gain of the first stage is 10 plus the noise figure at stage 3 is 5 minus 1 over 10 times A2, which is 25. Therefore, our noise figure is equivalent to 2.316. And solving for noise figure in dB, so we have 10 log of 2.316 is equal to 3.65 dB. So we have noise figure equal to 2.316, or in dB we have 3.65. Okay, so that is the noise figure. How about the noise temperature? How about the noise temperature of this amplifier? Okay, let me erase it first. So we have the equivalent temperature using the derived equation earlier. So we have noise temperature is equal to 290 times the noise figure minus 1. So 290 times our noise figure is 2.316. To substitute the value, so 2.316 minus 1. Therefore, our equivalent temperature is 382 Kelvin. That is the equivalent noise temperature of the amplifier having a 3-stage.